Yeah, I'm just here to give you a brief talk about various capability gaps that we have going forward when we're thinking about a Moon and Mars habitat. Um, I don't currently work in the space field. I was a NASA contractor for a year at the NASA Ames Center. I had the pleasure of working with Tomasz, who helped organize this conference, and he's really great, really smart. And I worked on an uh, microfluidic drug production device there, which I'll talk about briefly here. But right now I'm working in the pharmaceutical industry, and I recently quit a job working for Basira Biosciences. But I've always really loved space, really love learning about this type of stuff, and so I'm happy to give a talk on what a lot of other people are working on and what a lot of other people have been proposing for space habitats. So this is just to start with. This is a picture of Elon Musk's grand design for a city on Mars. This is a picture CGI of what he would like to do. And when you see something like this, as a scientist or engineer, you can think about, well, what about this can we do? What about the materials or the logistics or the things you want to do are actually possible with current technology and wouldn't require much invention or new design? And what about this can we not do? What are the things that we simply don't possess the capability to do that should be feasible, should be possible, but there's no devices or technology that currently exists for this? And I think that's a good frame to try and understand habitat design. But first, why strive for a habitat in the first place? Given that we can get a lot of great data with rovers and with unmanned missions. And I guess the best answer is that you can collect more data with astronauts. You can collect data on the effects of what these environments are on astronauts by having them in that environment. And I think the classic argument that you hear again is that by pushing technological boundaries, by having these challenging goals that force you to meet these capability gaps, you can then take these innovations and apply them to novel solutions for novel problem solving. The classic example being super resolution, which is an imaging technique that's used to clear up images to first from satellite images. So basically, you have a messy image, and you can use a super resolution algorithm to clean up that image and get more usable data from it. And that's used in all sorts of image processing on terrestrial applications, even though it was first used in a space environment. But really, when you're talking about capability gaps, the purpose of the habitat really defines what the design of the habitat is, and that defines what gaps that you need to make. The picture on the top here is a diagram of what, so I can't see the questions right now with the way I've set up my presentation, but I'll be happy to answer the questions at the end. The top here, you can see just a diagram of the Mars outpost that's proposed by NASA as part of the Artemis missions. And at the bottom, you can see Elon Musk's city. And you can obviously see just in terms of the scale, but obviously in terms of what is being done and the number of people, it's a very different thing and facilitates very different capabilities that need to be met. When you're looking at a city or something that's much larger, or a colony, let's say, as opposed to an outpost, it really can't be self-sustaining in terms of parts. There are lots of very complex technical either materials or components that need to be manufactured on Earth that are really not feasible to be manufactured on Mars for any long period of time. I'll talk about radiation mitigation and habitat design later, but even with the best designs, there's still going to be lots of cosmic radiation and radiation from the solar wind that's going to build up very quickly and exceed the lifetime radiation limits that are permissible for astronauts within a few years. And again, even if you could mitigate the parts and the radiation, how are you going to mitigate the fact that you're exposing people to microgravity for potentially years on end? And those are all capability gaps which are very difficult to meet, which are in addition you need to meet when you're talking about a colony as opposed to an outpost. I'll take a brief aside here to talk about the Artemis program, which I'm sure you're all familiar with, because it's basically building two different habitats, not on Mars, but on the Moon. And there's differences and different challenges when you're looking at different environments, whether you're looking at the Moon or Mars. For the Moon, it's much closer, obviously, and for Mars, you have potentially a 2-year gap between when you can deliver materials. And so materials that you could feasibly deliver every month to a monthly to a lunar colony. You wouldn't be able to do for a Mars colony. In addition, the soil on the moon can potentially be processed into building materials, and the ice can be more readily transformed into usable water and material. But both the soil and the water on Mars has perchlorates on it and would need to undergo further processing and treatment before you'd be able to use it. But we talk about Artemis as a platform to get to Mars, because it's kind of crazy to talk about building a Mars outpost before you even build a moon outpost, considering how much more difficult it is to actually send people to Mars and actually get them back, just in terms of the materials, but also in terms of the additional complexities. And in terms, after the Artemis program, which will be probably the first manned outpost on the moon, there are probably going to be other potential outposts that have been proposed. There'll probably be more than one moon outpost at the South Pole. And so we will see basically different lessons learned through different designs that are applied in different habitats. And so all of these will be used to inform a Mars outpost, because, like I said, the challenge will be greater. So we're talking about capabilities and capability gaps. So what capabilities do we already have, or do, I guess in my personal opinion, not speaking for NASA, feel that we could probably scale up or do within a few years, or are already in the pipeline? And I think food storage and hydroponic food growth in terms of scaling up is possible, but like I said, it needs to be further implemented on. Energy production from portable nuclear energy reactors seems to be a feasible way to produce constant energy regardless of where the light is or the given environment, and to be stable and efficient, and which hasn't been done before, but the technology seems to be there for that. And of course, for decades, NASA's been using drones, rovers, and manned vehicles to facilitate exploration. There's no reason that we would stop doing that just because we have people on Moon or Mars. It'd be easier to do those kinds of studies if we have people on place. But what capabilities do we really lack for Mars? And I guess there's probably many more than these, but when I was looking through literature and preparing for this, I came across this sort of list of things that we really do need, that we probably can meet, that they're feasible to do all these capabilities, to meet these capabilities, but that the devices or the proposals currently haven't settled on a single solution. And that would be water and fuel production and I'm talking specifically for Mars in this case, because I've talked a lot about the moon so far. But in terms of water and fuel production from the ice of the poles of Mars, we know that there's lots of water on Mars. We could potentially turn that into fuel with hydrogen, or to oxygen with cracking it. But in terms of taking that water and actually purifying it and then treating it so it can be used and turned into using the water cycle, like using the ISS, requires additional work. Same thing with air purification for habitats on Mars, with nitrogen compression and oxygen from CO2 on Mars. And additionally, there needs to be habitats that need to be designed that are suitable for long-term radiation exposure. These big buildings that are exposed to the Martian sun probably wouldn't be suitable for the amount of radiation that people would be exposed to. In addition, how these habitats are designed needs to be in such a way that the Martian dust can't enter inside of the habitat. So you can't have people entering inside and out of doors or through airlocks in any way, because dust would then enter into habitable areas. And lastly, which I'll talk about hopefully with my brief experience, is in situ production of degradable mission materials. Because if you're 2 years on a Mars mission versus 1 month, let's say, on a moon mission, the number of medicines or materials that we expect to be resupplied if we were on the ISS, we can't expect at all to be able to be resupplied. And some of those mission materials include degradable medicines. So first of all, in terms of air, in situ resource utilization, there's currently on Perseverance a system called MOXIE, which takes CO2 from the Martian atmosphere and produces about a tree's worth of oxygen from it. And theoretically, this can be scaled up to produce enough oxygen for a habitat. So in terms of oxygen, technology seems to be going there. But we additionally also need nitrogen compression, because air is not just oxygen. You need to dilute that with nitrogen, and we need to compress the nitrogen that's on Mars into a suitable form. And the device that does that and the habitat that does that needs to be designed. The water in situ resource utilization, there needs to be, because the water is lost in this water cycle, as you can see on the right here, based on the ISS. Even if you're trying to capture as much water from a habitat as you can, you're still going to lose some, and so you need to replenish your water, either by sending it via a rocket or getting it while you're there from Mars itself. There's lots of water in terms of ice, but also in terms of the minerals or perchlorates, or not perchlorates, but other sort of substances that water is trapped in. And so you need to be able to crack it to basically extract the water from that and treat it so that it will be acceptable, so that it can be put into this water cycle and be able to be used by the people on Mars to drink or to use in hydroponics. And again, this is all very theoretically possible. There's lots of water. We understand the chemistry of this, but to actually implement the devices to do this is another matter. Third, radiation limits, what's actually feasible. On Mars, as opposed to Moon, you have much more exposure to cosmic radiation from cosmic rays. And very quickly, you will see what's permissible for an astronaut. There have been proposals to put basically water emitters on the surfaces of habitats so that they be covered in ice, because ice is good at insulating from radiation. You can additionally, like I said earlier, cover these habitats in regolith. But again, exactly how you implement these things and how you put this into a working research outpost, remains to be seen. Additionally, and which maybe not talked about a lot in terms of, we know that Martian dust is very fine and it's full of perchlorates, but when you think about the actual implementation of day-to-day life, if the dust gets inside of habitats, it can be extremely harmful. It can be very hard to get rid of because now it's inside of the habitat. And so you need to think of ways to design spacesuits or basically a way to make sure that no dust can get inside the habitat in any way. There are these things called suit locks, which were designed by NASA in the 2010s for other purposes, where basically there's a suit on the outside instead of an airlock, so that you can just get inside the suit and leave out of the suit without ever really having to, get outside of it. So you have no chance of bringing dust inside. And again, this is all feasible. It definitely seems possible. It just needs to be implemented and designed. The thing which I don't know how much time I have left, but I'll try to talk a little bit more detail about in terms of capability gap is the in situ production of materials.
Patrick, hi, 3 minutes still.
Okay, great, thanks. So in terms of this, astronauts need to take teriparatide and HCCSF in order to help prevent bone degradation and radiation damage. It's basically a long list of medications that astronauts either take daily or optional, and those are some of the peptide or sort of unstable drugs that are on that list. And the problem with this is that, well, it's not a problem on the ISS because there are continual shipments of medicine and supplies for what they need. But if you're talking about a moon colony, which is going to be weeks away, or you're talking about a Mars colony, which is going to be much farther away, these peptide drugs need to be refrigerated. And even if they are refrigerated, they're going to still expire. So you need in situ production capability for these molecules. So basically, how do we do that? Because if you can't do that, you can't provide these astronauts these medicines, and they're going to get sicker while they're in space. And it's already a very taxing environment when you're in space, and you don't want to be cutting corners with your astronauts' health. There is capabilities to sort of make these in situ production pharmaceutical machines, like this refrigerator thing you see on the right, can basically produce a couple of different drugs just according to what you tell it to do. But the problem is it's kind of the size of a refrigerator. It needs to be miniaturized. It needs to be basically turned into a form that can be used and is feasible for a space environment. And which, of course, use miniaturization and a lot of different things. And it needs to be able to produce one dose of the drug per astronaut per day, because that's what the astronauts take. And this is basically, we came about basically a 3-step designed to basically produce this. It was, we called it the astropharmacy, and we produced a prototype that produced it, produced the peptide in a TXTL solution, basically composed of cell lysate, an energy solution with ATP, and then a DNA template that is just a plasmid for teriparatide or GCSF. And so in that cell lysate solution, you'll have transcription, you'll have translation from the DNA template, and you'll get your peptide. These peptides naturally fold into their final forms, or their final conformations, I should say. And then we did a two-step purification with connected in subsequent devices to basically purify the peptide in the device using his tags that we then cleaved off, and then using a size-based purification column where we also did a buffer exchange. And this is, I should say, it's a microfluidic device that we designed. This was over the course of like a summer, but it was, I think it was pretty cool work. I think we were able to produce both peptides in ready-to-use buffers. We didn't think about the system in terms of reusing it. So every time that we wanted to sort of make another batch, we had to like clean the device out. So we would need to make a version of the device that would essentially be reusable, or that would have a way of cleaning it out before and after each use. But in the way we use the system, in the batch system we had, we were able to produce peptide and produce it reproducibly, but we still need a way to increase the amount we did produce with the system, and as I said, make it reproducible. And this is a diagram of the system, so I don't have a picture of it with me right now. I wasn't able to find that, but it just essentially we produce it in a cell-free solution and we purify it, sort of how you purify any protein on a bench, except we're just doing it in a microfluidic system. And that's basically it. Like I said, there's lots of capability gaps that exist. And when you really go into the details and you start to think about how you do these things, there's many, many gaps because there's a lot of assumptions that we have from the ISS, and we can't take a lot of the assumptions from how we do things on the ISS and apply them to a Mars environment because of the differences and the 2-year gap. So I think that's pretty much all I have to say, and thank you all for your time.